This video is the first of two videos on the last learning goal of our reactions in stoichiometry unit. Learning goal 5.3 is classifying reactions, and this video will cover the first two success criteria A and B. As you can see from our learning goal here, 5.3 is to understand how reactions are classified. And our two success criterion A, I can model the 5 reaction types. And success criterion B, I can classify reactions by type. So there are many different ways of classifying reactions. This video will just take a look at one of the ways that we can do that. And in this particular method of classifying reactions, there are 5 basic types of reactions, which are, in no particular order, synthesis, decomposition, single displacement, double displacement, and combustion. Now, these 5 classifications of reactions work very well for classifying simple reactions, which is generally what we are learning about in this class. Over the course of your study of chemistry, whether it be in this class or if you take future chemistry classes, you will certainly find many reactions that do not fit neatly into any one of these categories. Like we said, this is just one way of classifying reactions. The more chemistry you learn, you will learn other ways of classifying reactions. And some reactions simply just don't fit into neat categories anyway. But these classifications allow us to get a good understanding of the possibilities of basic chemical reactions. And as you'll see in the next video, it allows us a way that we can go through a process to predict the products of reactions. Because if we understand the basic patterns of these reaction types, we can look at the reactants in a reaction and we can predict what the products are likely to be. So each of the next slides will cover each of those reaction types. So the first one there is a synthesis reaction. So synthesis reactions, this is whenever we have 2 or more reactants forming one product, just a single product. So the easiest way to identify synthesis reactions is to see that there is just a single product that is being formed. If you were to model this, and notice our learning goal here at the top, I can model the 5 reaction types. One way of modeling reactions is to simply write out a generic equation or a general equation that shows what the equation for that reaction type would look like, regardless of what the actual reaction is. So in a synthesis reaction, we are going to take at least 2 reactants, in this case represented by the letters A and B. Now those could be individual elements, they could be compounds, but the process that makes it a synthesis reaction is that those 2 reactants form just a single product where they come together. So for example, here are a couple of examples of synthesis reactions. Would be the formation of water, where I take hydrogen and oxygen, so 2 individual elements, and they come together to form a single product. Now the fact that I need 2 molecules to balance the equation does not make this not synthesis. In other words, when we say one product, if the stoichiometry or the balancing gives you something other than 1, that doesn't mean that it's not synthesis. We still just have a single product. We only get water. We don't get water and something else. So that makes this synthesis. Here's another example of a synthesis reaction where we have sodium and chlorine forming sodium chloride. And you can see the equation there. Again, the key is just one product. Now, whether we had 2 reactants or 20 reactants, as long as we just have a single product, like you see here, that would be a synthesis reaction. All right, the opposite of synthesis is known as a decomposition reaction. This is when one reactant is breaking down into 2 or more products. So it is the exact opposite of synthesis. So with synthesis, we said the key was to identify that there was just a single product. With decomposition, if we identify that there is just a single reactant, then we know we have decomposition. So the generic formula or the generic equation for the decomposition reaction is the exact opposite of synthesis, where I have a compound represented by AB. splits into two or more products. Now, in this particular generic equation, we're just showing the two products, but we could get more than that. So here are some examples. So we said it was the opposite of synthesis. So notice this example is the exact opposite of the first example from the synthesis slide, where water is breaking down into hydrogen and oxygen. Now again, like we said earlier, just because there is a stoichiometric coefficient of 2 here, or 2 molecules of water, does not mean that there's more than one product. More than one reactant in this case. In this case, the only reactant is water. Yes, it takes 2 molecules of it to make the reaction happen, but there's just a single reactant. Here's an example where we get more than 2 products, but the fact that we just have a single reactant, this ammonium carbonate, that whole thing is one compound. I can tell that because it's all written as one formula. There's not a plus sign in between there, so it's all one reactant. It's breaking down into multiple products, and notice something unique here compared to the last example is my products here are actually compounds themselves. So we don't have to get individual elements as products. We could get compounds as well. Alright, the next 2 slides look at the displacement reactions, the first of which we call a single displacement reaction. So in a single displacement reaction, a free element replaces a like charged element in a compound. The generic form of the equations that we could write here, and I have 2 different examples and you'll see why, is we have a free element, and in both cases the free element is listed with the generic symbol A. So this would represent any element that's by itself. It's not in a compound with something else. And it is reacting with a compound. So notice in this case the compound is represented by BC in both of the examples. Depending on the identity of A could take the place of B, as I'm showing here, and then B gets kicked out by itself. So notice my product here is AC, because A took the place of B. So I now have AC, and then B is now a free element as a product. Or A could take the place of C, and notice I now have BA as my product, and C gets kicked out by itself. Now, remember the importance of how we write formulas. Whenever we write the formulas of a compound, in this case represented by the generic symbol BC, the first element is always the cation, the positive ion. The second is always the anion, or the negative ion. So whenever we write the generic formula BC, we're saying B represents the cation, C represents the anion. So if A will form a cation, a positively charged ion, it will take the place of B. If A will form a negatively charged ion, an anion, it will take the place of C. And so I'll show you some examples here where we can differentiate between this. So this first one here, we have barium. Barium is our free element. It's by itself. It's not in a compound with anything else. It's reacting with sodium oxide. Well, barium is a metal. It's in group 2. It will lose 2 electrons when it forms an ion, so it will form a cation. So it's going to take the place of the cation in the compound, which is sodium. And again, I know that because it's written first in the formula. So the barium takes the place of the sodium. You'll see that over here. And the sodium gets kicked out by itself as a free element. In the second example, notice our free element here is chlorine. Well, chlorine is a nonmetal, so it's going to gain electrons when it forms an ion. So it will be an anion. So it's going to take the place of the anion in the compound here. So the chlorine will take the place of the bromine, and notice the bromine has now gotten kicked out as a free element by itself. Now, one thing you might be wondering is, looking at these equations, how I get these formulas here. Like, for example, I go from Na2O to BaO. Why not Ba2O? You might be saying the equation isn't balanced. And yes, you're absolutely right. These equations, as I have written here, these are not balanced. We can easily do that if we wanted to. But the important point to make here is this, that whenever we write these formulas, we have to write the formulas to be the actual formulas of the compounds. In other words, I can't just look at the subscripts over here and use those same subscripts here, because the formula for barium oxide is BaO. I know that because barium is 2+, Oxide is 2 minus, so I need one of each ion so the charges cancel. Okay, likewise, sodium is not diatomic, so I don't write Na2 just because I have a 2 here. And you can see on this example here, it's not KCl2 just because I have a Cl2 here. Chlorine is diatomic, meaning when it's by itself, it will be a 2-atom molecule, thus Cl2. But potassium chloride, the formula is just KCl because potassium is 1 plus, chloride is 1 minus. Likewise, bromine is diatomic, so when it's by itself, I write Br2. When it's with potassium, because of the charges, again, 1 plus, 1 minus, it's just KBr. Alright, so if we have single displacement reactions, we probably also have double displacement reactions, and that is in fact the case. So a double displacement reaction is whenever we have an ion exchange between two ionic compounds that happen to be in solution, so they're dissolved. And so here's a general form, a generic equation of this. And notice what we have here. We have two compounds, AB representing one compound, CD representing another compound. And all that happens is the ions exchange partners. And again, recall from the last slide, the order that we write the formula in makes a huge difference. It matters. A is the positively charged ion in this compound, and B is the negatively charged ion. Likewise, same thing over here. C is the positive ion, D is the negative ion. When these ions exchange, they must match up with an ion that they can actually form a compound with. In other words, positive must go with negative. So the easiest way to look at this, I think, is just to think about the cation switching places, where A, the positive ion in this first compound, takes the place of C, the positive ion in the second compound, and vice versa, where C takes the place of A. So notice we end up over here with AD, positive ion, negative ion, because it came first, and D came second. And then over here we have CB. No, not BC. I can't just write it in alphabetical order. It has to be CB, because C is the positive ion, and B is the negative ion. Now, in these examples that I'll show you, there are really three different ways that these double displacement reactions can occur. The first one is oftentimes known as a precipitation reaction. Precipitation because we get a solid coming out of solution. So notice just looking at the formulas here, that with these formulas I've included physical states of the substances, and with these double displacement reactions that is important. You'll see here I get a solid that has come out of solution, because both of my reactants are aqueous, meaning they're dissolved in water, and one of the products here is insoluble, meaning it will not dissolve in water, thus I get the solid. So notice how the ion exchange works here. The copper and the sodium have essentially just flipped places, where the copper is now in a compound with the phosphate ion, thus we get this copper 2 phosphate, and the sodium is now in a compound with chlorine, thus I get sodium chloride. Again, notice, like I mentioned on the last slide, when we write these formulas, and this comes more in the next lesson, in the last video for the unit, I'll give you a lot more detailed examples on this, but notice how the formulas, I cannot simply use the same subscripts I use over here, because I have to write the formulas correctly. The formula for this copper 2 phosphate is not just CuPO4, because that's what I see on the left side. I have to consider the charges, where the copper 2 is 2 plus, the phosphate's 3 minus, so this is Cu3PO42. You get the charges to cancel. Same thing with the sodium chloride. It's not Na3Cl2 just because those are the subscripts here. It's simply NaCl because the sodium's 1 plus and the chlorine is 1 minus. Alright, so that's a precipitation reaction whenever we get a solid coming from solution. Another sort of double displacement reaction is whenever we have an acid reacting with a base. And whenever this happens, we will always get water as one of our products, and I'll show you why. So an acid, and we've learned a little bit about acids as far as the nomenclature, how they're named, and one of the things that we mentioned was that they always contain hydrogen. So hydrogen is the cation in an acid, it's the positive ion. In a base, the anion is often the hydroxide ion, OH. So when you put these together, when the hydrogen switches places with the potassium to give us hydrogen hydroxide, HOH, well, the way we always write HOH is not that. We write it as H2O, it's water. So we get water as a product of these acid-base reactions, and then we'll also get some other salt. Salt not meaning the salt you put on your food necessarily, although it could be. The salt is just any ionic compound, where notice I get the potassium now that's in a compound with the sulfate, so potassium sulfate. And the water is just going to be a liquid. Notice we don't write aqueous, because water doesn't dissolve in water, it's just liquid water. So that's why we have the L there. The third sort of double displacement reaction is whenever we have a gas-forming reaction, and this will happen whenever we have an acid that reacts with a carbonate or a bicarbonated compound. So an example I have here is acetic acid. That's the HCH3COO. This is the acid that's in vinegar, reacting with sodium bicarbonate, where HCO3, that's the bicarbonate ion. If you look at your polyatomic ion chart, you'll see it listed there. It has the name hydrogen carbonate, also called bicarbonate. Now you might be looking over here at the products thinking, now wait, how is this double displacement? I actually see 3 products here, not just 2. Whereas my generic form here for double displacement should just give us the 2 products. Well, let's examine this to figure this out. So notice the sodium has taken the place of the hydrogen ion in this first compound. So I now have sodium acetate, and that matches what we would predict, where the sodium takes the place of the hydrogen. On the other end of it, you might be thinking, well, wait, the hydrogen should take the place of the sodium, and that would give me hydrogen carbonate, which would be H2CO3, because the hydrogen ion is 1+, and this carbonate, CO3, is 2-, so I need 2 hydrogens. I should get H2CO3. Well, what really happens, though, is that whenever that H2CO3 forms, it actually just breaks apart into water and carbon dioxide that you see here. You'll notice if you examine this equation that if you put that together, H2O and CO2, there's 2 hydrogens, a carbon, and 3 oxygens. So that matches that H2CO3 that we might predict. So anytime we have an acid, and again, a good way to identify acids is whenever the formula starts with a hydrogen, and H. If we have any sort of acid reacting with a carbonate, whether it be HCO3, which would be bicarbonate, or carbonate itself, which is just CO3, we will always get water and carbon dioxide as products in our reaction. Okay, last reaction type here is known as combustion reactions. Combustion reactions occur whenever any compound or element burns in air. And recall that whenever something burns in air, that simply means it's reacting with oxygen. So in this generic equation, I have AB as some generic fuel, whatever's being burned, and then O2, that has to be a reactant. So the giveaway for combustion reactions is whenever you see O2 as a reactant. So if a compound burns in air, what we're going to get is a combination of oxides made from that compound. So notice AB contains generically the elements A and B. We're going to get some oxide of A, so AO, and we're going to get some oxide of B, meaning BO. When we say an oxide, it just means a compound that contains oxygen with another element. So here are a couple of examples. The first one is the burning of sodium in air, so reacting with oxygen. So Na plus O2, and notice we get sodium oxide. We get an oxide of sodium. Now you might also recognize that this particular reaction is also a synthesis reaction. So if you were classifying this and you saw this equation, you would need to classify it as both synthesis and combustion. Synthesis because we get the one product, combustion because O2 is a reactant. Here's a second example of a combustion reaction, and again, what's the dead giveaway for a combustion reaction? We see O2 as a reactant here. Now notice in this case we're burning a compound. This is methane, CH4, and I get 2 different oxides. I get an oxide of carbon, which is carbon dioxide. That's the most common oxide of carbon. And then I get an oxide of hydrogen, because my 2 elements in methane are carbon and hydrogen. So I get an oxide of carbon, I get an oxide of hydrogen, which that's just water. Okay, the most common oxide of hydrogen is water, so that's what we get. Okay, so you've seen examples of each of the 5 reaction types here. What I want you to do on this slide is pause the video and look at each reaction there, the equations written, and you'll notice they're not balanced, but that doesn't matter. And look back at your notes and identify each of these equations, each of these reactions as one of the 5 reaction types. So you'll tell me, is it synthesis, decomposition, single displacement, double displacement, or combustion? And then once you've done that for each, go ahead and play the video and see how you did. Okay, so you had a chance to do this, so I'll just talk through each of these solutions here real briefly. So the first one is single displacement. I know this because I have a free element that's taking the place of an element in a compound. Notice the copper takes the place of the silver. The silver now gets kicked out by itself, so it's single displacement. Number 2 is double displacement because I have ion exchange. Notice the silver is taking the place of the sodium to form silver chloride. The sodium takes the place of the silver to form sodium nitrate. So that's double displacement. The next one would be both synthesis and combustion. Synthesis because we get just a single product here, the copper 2 oxide. Combustion because O2 is a reactant. So we would need to list both there. Number 4 is single displacement. Notice I have a free element, in this case fluorine, taking the place of an element in a compound, in this case bromine. The bromine has now gotten kicked out by itself. So I now have sodium fluoride instead of sodium bromide, and I now have bromine as my free element. The next one is decomposition. The giveaway here is a single compound being a reactant, splitting up into 2 or more products. So I have decomposition. That's single reactants, the giveaway there. The next one is combustion. Again, the giveaway here is O2 as a reactant. Sometimes, and I understand why, students will confuse this for single displacement. Notice if you compare this one to the one 2 above it, the reactant side looks very similar in that we have a compound reacting with a free element. But notice on the product side, I don't get a free element as a product. Anytime we have single displacement, if you look at the first example, there's silver, that's a free element. On the second one, on the next one, that was single displacement, bromine is a free element because it's not in the compound. If I have a single displacement reaction, we'll always have a free element as a product. Here we don't have a free element. I have 2 oxides, one of nitrogen and one of hydrogen. I get nitrogen monoxide and I get water, and the fact that I see O2 as a reactant there makes it combustion. Okay, and then the last one there is decomposition. Again, what the giveaway here is, I just have a single reactant. Again, this whole thing, even though, yes, there's multiple elements in it, that whole thing is just one reactant, it's one substance. It's a single formula. Notice it's breaking apart into more than one product, so that is decomposition. All right, that concludes this lesson. Looking at our success criteria here, we looked at modeling the 5 reaction types, and we looked at classifying reaction types, and you'll notice on the worksheet that goes with this video that you will get plenty of practice in that classifying of reaction types.